Morning. Okay, in the um, last classes we discussed about the classes of FFT, that is radix 2, DAT FFT, dimension in time FFT, dimension in frequency FFT, their properties, and some problems related to DAT FFT and DAF FFT. Right. Next, we are going to start the next unit, that is review of jet transforms. Review of jet transforms. Okay, review of jet transforms. Right. Here we are going to see the realization of digital filter structures. Realization of digital filter structures. Okay, how these digital filters can be realized? So these can be realized by the following two realization techniques. We have two realization techniques. What are those two realization techniques? So those are recursive realization and non-recursive realization. This recursive realization is also called as IIR digital filter structures. Recursive realization or IIR digital filter structures. Second one is non-recursive realization, or it is also called as FIR digital filter structures. Okay, this recursive realization is also named as IIR digital filter structures, and non-recursive realization is also named as FIR digital filter structures. Okay. Next, coming to the recursive realization. What is meant by recursive realization? So here, recursive realization is simple. It is nothing but the current output y of n. Suppose if you take y of n is the output, the current output y of n is a function of present input, and past output samples. Right? Present input, and past input samples. Okay, past output samples. Right? So the present output y of n depends upon the present input, past input, and past output sample. Suppose x of n is the present input, x of n minus 1, n minus 2, these are the past inputs. Similarly, y of n minus 1, n minus 2, these are the past outputs. So y of n is the present output. So present output depends upon the present input, and past output samples, right? So for example, it is represented by y of n equal to x of n, x of n minus 1, x of n minus 2, and so on, and y of n minus 1, y of n minus 2, and so on, right? This realization corresponds to IIR digital filter structures. Okay, this is called a recursive realization. Recursive realization means here the output present present output y of n depends upon present input, past inputs, and past output samples, right? So next, coming to the non-recursive realization. So non-recursive realization means here the current output y of n is a function of present and past input samples. Present and past input, that is x of n and x of n minus 1, n minus 2, etc. Okay, this realization corresponds to FIR digital filter structures, right? So, for example, it is represented as y of n is equal to x of n, x of n minus 1, x of n minus 2, x of n minus up to x of n minus n. So, in recursive realization, the output y of n depends upon the present input, past input, and past outputs. Whereas in non-recursive realization, the output present in output y of n depends upon the present input and past inputs samples. Okay, so now recursive realization is also named as IIR digital filter structures, and non-recursive realization is also named as FIR digital filter structures. Okay, so IIR digital filter structures are recursive realization techniques. So here, what are the techniques involved in this recursive realization and are IIR digital filter structures? So there are 7 well-known to realization IIR digital filter techniques. So those are direct form 1. First one is direct form 1. Second one is direct form 2. It is also called as a canonic or minimum number of canonic or minimum number of memory locations required realization technique. Third one is transposed realization. Fourth one is cascade realization. Fifth one is parallel realization. Sixth one is lattice realization, and last one is ladder realization. These are the 7 techniques of recursive realization. First one is direct form 1. Second one is direct form 2. Third one is transposed realization. And fourth one is parallel realization, cascade realization. Fifth one is parallel realization. Sixth one is lattice realization. And the seventh one is ladder realization. So one by one I will explain. Okay. So first one is direct form one realization technique. Direct form one realization technique. So here let us consider a system IIR digital filter described by nth order, nth order linear constant quotient difference equation LCCDE. So nth order LCCDE, that is linear constant quotient okay difference equation LCCDE is given by, already we discussed in second unit. Okay, so y of n equal to minus sigma k equal to 1 to n ak into y of n minus k plus sigma k equal to 0 to m bk into x of n minus k. This was already discussed while discussing the DFT, discrete Fourier transform. Okay, concept, right? So this is called nth order LCCDE, that is linear constant quotient difference equation. Linear constant quotient difference equation LCCD is given by y of n equal to minus sigma k equal to 1 to minus sigma k equal to 1 to n ak into y of n minus k plus sigma k equal to 0 to m bk into x of n minus k. That let it be considered as equation number 1, right? Equation number 1. Okay, next this can be written like this: y of n equal to, here k is varying from 1 to n, here also k is varying from 0 to m. So it can be written as minus a1 into y of n minus 1 minus a2 into y of n minus 2 plus dash 2 dash 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 plus a n minus 1. Similarly, y of n minus n minus 1 minus a n into y of a n minus 1 to y of n minus 1 minus a n into y of n minus n plus b naught into x of n plus b1 into x of n minus 1 b2 into x of, like this we can write uh, for k equal to 1 to n summation and k equal to 0 to m summation. Let it be considered as equation number 2. Consider omega of n equal to b naught into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2 and so on, b of m minus 1 into x of n minus m minus 1 plus bm into x of n minus m. So this is considered as omega or w of n. So this is considered equation number, okay, equation number 3, right? Equation number 3. Next, so this is first of all we have to take the nth order LCCD equation, that is linear constant quotient difference equation. Linear constant quotient difference equation, that is y of n equal to minus sigma k equal to 1 to n ak into y of n minus k plus sigma k equal to 0 to m bk into x of n minus k. Let it be expanded. That is equation number 2. Consider w of n equal to b naught into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2 and so on plus bm minus 1 into x of n minus m minus 1 plus bm into x of n minus m. Okay, that is w of n, right? And y of n, will become e minus a1 into y of n minus 1 minus a2 into y of n minus 2 up to a n minus 1 into y of n minus n minus 1 minus a n into y of n minus 1 plus this bn terms, all bn terms will be considered as w of n, okay, plus w of n. Let it be considered as equation number 4. So equation number 3 can be realized by using direct form 1 realization like this following figure. Okay, so this is x of n. Equation 3. What is equation 3? That is w of n is equal to b naught into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2 plus dash 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 dm into x of n minus 1. So it can be written like this. So this is x of n into b naught. Okay, x of n into b naught into x of n. That will be summated. This is summer. Okay. Mm, plus b1 into x of n minus 1. See the equation number 1. b1 into x, equation number 3. b1 into x of n minus 1 plus b2 into x of n minus 2, right? So b1 into x of n minus 1, b2 into x of n minus 2. Okay, this is z inverse, okay. So these all will be added. b2 into x of n minus 2, bm minus 1 into x of n minus m minus 1 plus bm into x of n, all will be added. Okay, so these will be added. So this will be equal to w of n. This w of n will be added to minus a1 into y of n minus 1. Okay, y of n minus 1 plus minus a2 into y of n minus 2. Okay, plus minus an minus 1 to y of n minus 1, n minus n minus 1, minus up to minus an into y of n minus n. Okay, so all will be summed and it will be equal to y of n. Like this in direct form 1, we can be arranged. This is called direct form 1. So first of all, xn into b naught plus b1 into x of n minus 1. How to get x of n minus 1? Z power minus 1 and x of n is nothing but x of minus 1, x of n minus 1. Okay. Similarly, z power minus 1 and x of n minus 1 is equal to inverse z transform. This is x of n minus 2. Okay. So b2 into x of n minus 2. In the same manner, this a1 minus a1 into y of n minus 1. Okay. Similarly, minus a2 into y of n minus 2 minus a power a n minus 1 into y of n minus n minus 1 minus an into y of n minus n. Okay, so all will be added. This is w of n plus this one is equal to y of n, right? So this is a direct form one structure of equation number 4 can be realized as shown in figure B. So this is figure A and this is figure B. Okay, figure C is nothing but direct form one structure of the entire equation of uh, entire equation number 4. Okay, this is the direct form 1 structure. So the above structure is called direct form 1 IIR digital filter structure, which is used to separate delays for both input and outputs. We use it to separate delays for both input and outputs as shown in the above figure. This realization requires total number of multiplications m plus n plus 1. Okay, total number of the multiplications m plus n plus 1. Okay, so the total number of additions required is m plus n. The total number of memory locations required is also m plus n. Is it clear? Direct form 1 is clear. So simply we are writing this. This is the equation. This equation can be arranged in this structure, direct form 1 structure like this. Okay, this is the direct form 1 structure. Okay. Next, coming to the second one is direct form 2. Direct form 2, or it is also called as canonic or minimum number of memory locations realization. This is a direct form 2 or canonic or minimum number of memory location realization. So let us consider a system that is IAR digital filter described by nth order LCCDE. There is linear constant coefficient difference equation is a same equation. Y of n equal to minus sigma k equal to 1 to n a k into y of n minus k plus sigma k equal to 0 to m bk into x of n minus k. This is equation number 1. For this, we are going to apply the Z transforms on both sides. So by applying Z transform for y of n, that is y of z, so it is sigma k equal to sigma k equal to 1 to n a k into y of n minus k into z power minus k plus sigma k equal to 0 to m bk into x of z into z power minus k, right? of z into z power minus k. Okay, so it will become y of z. Y of z, already y of z is there. Y of z here is there. So taking y of z as common, this will become 1 plus sigma k equal to 1 to n a k into z power minus k is equal to sigma k equal to 0 to m b k into x of z into z power minus k. Okay, x of z into z power minus k. Okay, so that you can write the transfer function y of z by x of z, that is h of z is equal to sigma k equal to 0 to m b k into z power minus k by 1 plus sigma k equal to 1 to n a k into z power minus k, or h of z is equal to y of z by x of z. We can write this as y of z by w of z into w of z by x of z. Y of z by w of z equal to sigma k equal to 0 to n bk into z power minus k. Okay, bk into z power minus k. Y of z by w of z equal to sigma k equal to 0 to m bk into z power minus k. So y of z by cross multiplying this one, we will get y of z equal to w of z into b naught into z power 0 plus b1 into z power minus 1 plus b2 into z power minus 2 and so on. Right? Then y of n equal to y of n. Y of n is nothing but inverse z transform of this one. Inverse z transform of this one. Or y of n is this one. So from this also we can write y of n as w of n into b naught plus w of n minus 1 into b of b1 plus w n like this. We can write y of n. So w of z by x of z is equal to 1 by 1 plus sigma n equal to 0 to n into a k into z power minus 4. We can write uh, this equation from this expression x h of z equal to y of z by x of z, that is sigma k equal to 0 to m b k into z power minus k by 1 plus sigma k equal to 1 to n a k into z power minus k. This is 1 by 1 plus sigma k equal to 1 to n a k into z power minus k, right? Now w of z into 1 plus sigma cross multiplication. So sigma k equal to 1 to n a k into z power minus k equal to x of z, right? But w of z is equal to w of z multiply w of z with this expression, so it will become w of z plus sigma k equal to 1 to n a k into z power minus k into w of z is equal to x of z. Now we will apply inverse z transform for this expression, so that we will get inverse z transform of w of z plus sigma k equal to 1 to n a k into z power minus 1 into w of z is equal to inverse z transform of x of z. So inverse z transform of x of z is nothing but x of n. Inverse z transform to w of z is nothing but w of n, right? W of n minus k is this is frequency shifting property. Z power minus k into w of z, and inverse z transform of y of z is y of n. Okay, so this is w of n, w of n plus sigma k equal to 1 to n a k into this can be written as a k into z power minus 1 into z power minus k. Z power minus k and w of z can be written as w of n minus k. So a k into w of n minus k equal to x of n, or w n is equal to x of n minus sigma k equal to 1 to n a k into w of n minus k. So w of n equal to x of n minus a1 into w of n minus 1 minus a2 into w of n minus 1, like this. Okay, a2 into w of n minus 2, like this, a n minus 1 and w of n minus n minus 1 plus a minus a n into w of n minus n. This is considered as equation number 1, or y of z by w of z is equal to sigma k equal to 0 to m b k into z power minus minus k, or y of z equal to w of z into. So this can be written as bk into inverse by applying inverse z transform. This is z power minus k and w of z will become w of n minus k, right? W of n minus k. So y inverse z transform of y of z equals sigma k equal 0 to m bk into inverse z transform z power minus k into w of z. This will become w of n minus k. Okay, then y of n will become b naught into w of n plus b1 into w of n minus 1 plus b2 into w of n minus 2 and so on up to bm into w of n minus 1. That is equation number 2. So equation 1 can be realized using direct form on structure as shown as equation number 1. So this can be realized by using direct form 1, that is a1 into w of minus a1 into w of n minus 1. Okay, so see here, minus a1 into x of n equal to x of n equal to x of n minus this one. So x of n, this is x of n minus a1 into w of n added minus a2 into w of n minus 2 added minus an minus 1 into w of n minus n minus 1 minus an into w of n minus 1. Okay, xn minus this one is equal to w of n, right? W of and v naught into w of n. This is y of n. Y of n equal v naught into w of n plus b1 into w of n minus 1 plus b2 into w of n minus 2 plus bm minus 1 into w of n minus 1 plus bm into w of n minus 1 will give y of n, right? So equation number 2 can be realized as shown in figure, right? So this is the figure. This is y of n and this is x of n. Y of n, x of n. This is direct form to structure. For n equal to m, if both n and m are equal, then we will add these two. Okay, so xn minus a1 into w of n minus a2 into w of n minus 2 minus an minus w of n minus 1. Okay, plus d naught into w of n plus b1 into w of n minus 1 plus b2 into w of n minus 2 plus bn minus 1 into w of n minus n minus 1 plus bn into w of n minus 1 is equal to y. Okay, so this is nothing but a direct form to structure for nth order linear constant coefficient difference equation. So this the above structure is called direct form to structure, which uses common delay factors both input and output side. By using this realization, we can reduce half of delay terms or memory locations. Okay, compared with the direct form and structure. Therefore, this realization is also known as canonic or minimum number of memory locations required realization. For this realization, the total number of multiplier required is equal to m plus n. Total number of adders are m plus n, and total number of memory locations are maximum of m and n. Maximum of m and n. Okay, this is a form two structure. So we will using form one, we can write separate structures, and if for n equal to m, we can combine these two. Okay, and form 3 is next technique. Third technique is transposed structure. What is that? Transposed structure. So here some steps are there. Okay, from the first one is from the given difference equation, we have to implement direct form to structure. That is the first step. From the given difference equation, we have to implement direct form to structure. Next, the second step is interchange input and outputs. Third step is reverse the direction of flow of signals. Reverse the direction of flow of signals. Okay, in the direct form to structure. Next, fourth one is interchange nodes and summing points. Okay, interchange nodes and summing points. Okay, so that is the transposed structure. So let us take the direct form to structure. interchange inputs and outputs. Okay, in COM2 structure, interchange inputs and outputs. So, and then third one is reverse the direction of flow of signals in the direct COM2 structure. Now, reverse the direction of flow of signals, and finally interchange nodes and summing points. Okay, interchange nodes and summing points, right? So that it will become transposed structure, right? So this is COM2 structure. So interchange, first of all, interchange y of n, we will interchange y of n here and x of n here. Okay, x of n and y of n will be interchangeable. What is the next step? Interchange inputs and outputs. Okay, inputs and outputs. Next, reverse the direction of flow of signals. So here the direction of flow of signals are like this. This is going out, this is going out, and here by interchange means coming in, coming inside, coming inside, coming inside. Okay. Next, fourth step is interchange nodes and summing points. See in the above diagram, these are the summing points and these are the nodes. So interchange nodes and summing points. So the summing point will come at here and node will come at here. This summing point will come at here and node will come at here, right? So interchange nodes and summing points. Okay. So these are the summing point will come at here. This is node will come at here. Okay. So this is the transposed structure of the above diagram. Okay. That is COM2 diagram, COM2 structure, transposed structure of the COM2 structure. Okay. That is the third technique. And fourth technique is cascade realization technique. What is that? Cascade realization technique. Okay. So here this cascade realization is implemented by attaching all the factors of the system function h of z is in series, that is cascaded. Okay, let us consider the nth order system is described by the system function, that is h of z equal to sigma k equal to 0 to m bk into z power minus k by 1 plus sigma k equal to 1 to n ak into z power minus k, right? Let the system function h of z is represented in the subsystems. Each subsystem's highest degree is 2. Each subsystem highest degree is 2. Okay. So that is h of z equal to phi of k is 1 to n hk into z, that is h1 of z into h2 of z up to hn of z. Okay. This is multiplication factor. Phi is nothing but multiplication. This is summation. This is multiplication. So multiplication of k is varying from n to n. Okay. It is equal to h1 of z into h2 of z into h3 of z into up to hn of z. N is integer part of n minus m by 2. Phi is product of subsystem of h of z. Okay. So hk of z is equal to d naught of k plus b1 of k into b1k into z power minus 1 plus b2k into z power minus 2 by 1 plus a1 into z power minus 1 a1k into z power minus 1 plus a2k into z power minus 2, etc. like this. Okay. So we can write this xk of n. Xk of n is first of all we will write individually and then add. Okay. So this is xk of n plus a1 into k plus b naught of k, b naught of k plus b1k into z power minus 1 plus b2 into z power minus 2. This is the numerator part. Okay. And the denominator part is 1 plus this is 1. 1 plus a1 into a1k into z power minus 1 plus a2k into z power minus 2. So this is hk of z, right? Hk of z. Okay. Hk of z is equal to yk of n by xk of n. That is nothing but hk of n, right? So this x of n will be taken as product of H1 object, H2 object, H3 object, like this up to Hn object, right? So that we can write like this. So this is X of n is the input, Y of n is the output, right? So H1 object, what is H1 object? This is a H1 object. H1 object into H2 object into H3 object, like this. So this will become product H1 object into H2 object into H3 object up to Hn object. So and this entire thing is a H object. Why? Because here H object equal to product of H1 object, H2 object, H3 object up to Hn object, right? So this is H object and its output is Y of n and the input is X of n. Like this, we can cascade these structures. So this is cascade realization technique. All these structures will be cascaded. Okay, that's why it is called cascaded structure, cascaded realization structure. Last 10 minutes is there. Okay, speed up, speed up the process. Okay, next technique is parallel form realization technique. Parallel form realization technique. What is parallel form realization technique? Parallel form realization is obtained by making use of partial fraction expansion of system function H object. How to get parallel form realization technique? So by making use of partial fraction expansion of system function H object. Let us consider mth order system which is described by H object, that is H object equal to Y object by X object, that is sigma k equal to 0 to m dk into z power minus k. For 1 plus sigma k equal to 1 to m ak into z power minus k can be written as equal to a plus sigma k equal to 1 to n ak by 1 minus ak into z power minus 1. Okay, so it is equal to a plus sigma k equal to 1 to n 1 plus 1 plus k k k of z. Okay, this is hk of z. This is hk of z. A plus sigma k equal to 1 to n hk of z. This is called hk of z. Alpha by 1 minus alpha. This is hk of z. Okay, so h of z equal to a plus sigma k equal to 1 to n hk of z, that is equal to a plus h1 of z plus h2 of z up to hn of z. Here a is bm by an. Okay, bm by an. How to add this form? So x of n is this one, a is this one, a plus h1 of z, h2 of z up to hn of z. These all will be summed and this is nothing but y of n. So y of n by x of n is equal to a plus h1 of z, h2 of z, h3 of z up to hn of z. This entire thing is h of z. These all terms will be, these all factors will be summated. Okay, so a is a, h1 of z, h2 of z, h3 of z, h4 of z up to hn of z. All will be added here. This is a summation factor. Okay, so this is parallel form realization technique, parallelly added. Okay, so hk of z equal to ak by 1 minus ak into z power minus 1. Okay, ak by 1 minus ak into z power minus 1. So this is xk of n, this is yk of n. A1, suppose if you take a1, h1 of z, a1 by 1 minus a1 into z power minus 1. Okay, so a1 is this one, ak into z power minus 1. Okay, this will be added. So a1 by 1 minus this is 1, 1 minus ak into z power minus 1. This is h1 of z. Like this, we have h2 of z, h3 of z, h4 of z, all are there. All will be represented like this. Okay, so these are the 7 techniques. These are the techniques used in realization techniques. Next, we'll do some problems. Realize the following systems. So first, the problem given is y of n equal to minus 3 by 8 into y of n minus 1 plus 3 by 32 into y of n minus 2 plus 1 by 64 into y of n minus 3 plus x of n plus 3 into x of n minus 1 plus 2 into x of n minus 2 by using direct form 1, direct form 2 and transposed structure. Okay, direct form 1, direct form 2 and transposed structure. Draw the structures also. Okay. The linear constant position difference equation is given like that, y of n. Okay, in direct form 1, y of n is given as minus 3 by 8 into y of n minus 1 plus 3 by 32 into y of n minus 2 plus 1 by 64 into y of n minus 3 plus x of n plus 3 into x of n minus 1 plus 2 into x of n minus 2. Let us take w of n as a x n terms. So x of n plus 3 into x of n minus 1 plus 2 into x of n minus 2 is considered as w of n. So y of n will become minus 3 by 8 into y of n minus 1 plus 3 by 32 into y of n minus 2 plus 1 by 64 into y of n minus 3 plus w of n. That is considered as equation number 2. So equation number 2 can be realized, or structure can be, you can draw the structure of form 1, direct form 1 as like this. So first one, omega n, w of n is x of n into 1, so 1 into x of n plus 3 into x of n minus 1 plus 2 into x of n minus 2, all are added. Okay, so that is w of n. This w of n will be added to y of n. What is y of n? Y of n, that is minus 3 by 8 into y of n minus 1 plus 3 by 32 into y of n minus 2 plus 1 by 64 into y of n minus 3. That is y of n. Okay. So w of n plus this thing is equal to y of n. This is direct form 1. This relation requires total number of multipliers is m plus n plus 1. So here 2 multipliers, here 3 multipliers. So 2 plus 3 plus 1, that is 6 multipliers. Okay, 6 multipliers. Then summers are m plus n. Right. So we have 5 summers. Memory locations are m plus n also. That is 5. That is form 1. Coming to the direct form 2 realization technique. Direct form 2 realization technique. So here also, here we have to apply the Z transform on both sides. Z transform on both sides, so that y of z will become minus 3 by 8 into z power minus 1 into y of z plus 3 by 32 into z power minus 2 into y of z plus 1 by 64 into z power minus 3 into y of z plus x of z plus 3 into z power minus 1 into x of z plus 2 into z power minus 2 into x of z, right? Taking y of z terms on one side and x of z terms on another side. So h of z equal y of z by x of z, that is this one. So y of z by w of z into w of z by x of z. So first of all, we will take the w of z by x of z equal to 1 by 1 plus 3 by 8 into z power minus 1 minus 3 by 32 into z power minus 2 minus 1 by 64 into z power minus 3. So that is equal to x of z by this one. So w of z into this cross multiplication. So x of z, w of z equal to x of z into x of z minus like this, multiply this one. So now apply inverse z transform for this one, so that we will get w of n equal to x of n minus 3 by 8 into w of n minus 1 plus 3 by 32 into w of n minus 2 plus 1 by 64 into w of n minus 3, or y of z by w of z equal to 1 plus 3 into z power minus 1 plus 2 z power minus 2. Okay, here also we will apply inverse z transform. Okay, that's why we will get y of n equal to w of n plus 3 into w of n minus 1 plus 2 into w of n minus 2. So for this we draw this direct form 2 structure. Okay, these multipliers are n plus n plus 1, so that is 6. So adders are 1 2 3 4 5. 5 adders are there. Okay, and memory locations are maximum of 2 and 3, that is 3 is the maximum number. Transpose structure. For this form to will interchange inputs and outputs. After that, interchange the directions. Okay. After that, interchange uh, the adders and nodes. Okay. This is the transpose structure. This is about this problem. Okay. In the next class, we'll continue the next problems. Okay. Thank you.